Hello everyone, welcome to another video. Now we're going to talk about the second surge of deep learning in NLP part 2. So far you've learned about all sorts of attention except for one, that is self-attention. This video, we're going to talk about self-attention. If you remember, we preserved the word self-attention for a specific type of attention that we're going to talk about throughout this video. Let's start with a quick definition. In self-attention, each word in the sequence is a representation of the entire sequence. We'll see shortly why that matters. One of the drawbacks of the recurrent neural networks is that at the time of reading, at the time of forming the representation from the words, or alternatively said, at the time of encoding, recurrent neural nets, even in the ones enabled with attention, they will have to read the tokens in the sequence one by one. That is, your x0 has to be processed before your x1, x subscript 1 can be processed and formed a representation of. That means if you have a sequence of length 100, you will only have a representation of the last word, the 100th, or with index 99, when you have gone through every word prior to it in the sequence. And that is not super efficient. And above all, that's not parallelizable. So self-attention is a mechanism to address just that. If we achieve that, then we can parallelize the processing of the entire sequence, given the parallel computing power that we have today, specifically in GPUs. Okay, let's get started. So let's take a look at the overall architecture of the self-attention network called the transformer architecture. This architecture is an encoder-decoder architecture. You are familiar with encoder-decoder architectures from the previous videos, where simply put, you're encoding your sequence with a module on the left, right? That's the encoder. And on the right, you can see the decoder, where you can decode your created representation and representations into a sequence or some sort of output. So just like any other encoder-decoder architecture, the transformer network simply takes the input and creates some sort of representation, then uses the acquired representation and generates a sequence of tokens or any sort of output. That's basically what it is at a high level. We'll get to the details in a second. So we have said earlier two important points about self-attention. One, mentioning that each word is a representation of the entire sequence. And two, that it improves over RNNs by parallelizing the processing of the tokens, of the input tokens. So let's conceptually connect the dots now, and you'll see the details in the later slides. So to be able to parallelize the sequence, the input sequence, the transformer encoder architecture takes each word individually in, but each word will be some weighted representation of the entire sequence, And that's how we achieve parallelization. And that's how we connect the dots. So basically, parallelization is possible because each word is aware of its entire context, of the entire sequence. So it's not in isolation anymore as far as network's understanding is concerned. Hence, enabling the network to process all the words at the same time. Your tokens over here are words, for example. They could be in discrete signals. and the sentence is, the French sentence being translated to English with an encoder-decoder architecture, being Je suis étudiant. Basically, the words going all at the same time, and the first sublayer of the encoder layer, called self-attention, the self-attention sublayer, creates representations for all of these words simultaneously. The self-attention sublayer is a linear layer. Therefore, we have a feed-forward sublayer following it immediately to add nonlinearities. All right, so let's take a look at the notation and parameters. So x sub I obviously is the ith item in the input sequence. Z sub I is the ith representation, immediate representation corresponding to the item I. Y sub I is your output I in the output sequence. The depth of your encoder and decoder modules of the transformer architecture are 6 each. The dimensionality of embeddings as well as each layer is 512. There are two types of sublayer, as you know so far, self-attention fully connected. You have residual connections after each sublayer. And for each sublayer, you have residual connection. So basically, let's say we're looking at the feed-forward sublayer over here. You have Z as input. So Z goes in to the feed-forward sublayer, and some processes will happen, and some output will be, generated out of the feed-forward layer. That output will be added to Z1, for example, directly as a skip connection. Now you see that a little bit later as well. Each sublayer also, so the output of the skip connection of this residual connection, both the representation coming out of the cell as well as the representation prior to the cell, they get added together, and there will be a layer norm upon them. You'll see them in a second as well. Regardless, so you have residual layers, and then you have the dimensionality of your feed-forward layer as 2048. Your input and output of feed-forward layers are 512, obviously. They have to match, the embeddings and intermediate representations. All right, so this is the layer norm we've been talking about. H over here is the size of the vector, which is your component size. And this component size is 512. So these vector sizes are 512, as mentioned earlier. And we're just, so alpha is your A is your activation, and mu and sigma are your mean and standard deviations, right? Okay, so in layer norm, basically what we want to do is we want to center the distribution of the layer and normalize it. So we want to have a zero mean and standard, unit variance, standard deviation of 1 as your standard deviation and variance. So basically, what you do is you add for each activation, you compute the mean of the layer for each for each layer. You compute the mean of the layer by summing up all the activations in that layer and dividing them by the size of the layer. As simple as that. You have the mean, then you can compute the standard deviation for the layer, just like this. Basically, you subtract the mean from all the activations in all the components of the layer, and sum them up, divide them by the size of the layer, and compute the square root of that, which is your basic standard deviation. So you have your mean and standard deviation. You can subtract the mean from each component. Basically each a sub I, superscript L of your entire layer, and divide again each component by the standard deviation to normalize the layer. So that's layer norm. On a high level, this layer norm helps keep the distribution of your entire layer under check and relative to each other and in a manageable range. Okay, now let's get into the details of the self-attention sublayer. So we're asking the question that how is it that each word is a representation of every other word, including itself in the sequence? The simple answer is via the following tools. So basically, we have three matrices, WQ, WK, and WV. And each matrix is responsible to give us a representation, a simple representation for the same word. So basically what we do to, this is all to parallelize, and things will come together in a bit. But let's take a look at the tools right now. We need three representations per word. Previously in the recurrent neural networks, we just had one representation per word. That was enough. But right now we need three. You'll see how. And this is the core of how we're able to parallelize the computation. We need these three, and we call them Q, K, and V. Per word, you have a query vector. You have you basically need a query vector. You need a key vector, and you need a value vector. Okay. To generate those, you need these three matrices as we spoke of earlier. So basically, what you do, you have some initial embedding representation. This could be randomly generated, or could actually use an embedding such as generated by Word2Vec or GloVe, as we have discussed earlier. Regardless, we take them as input. So we look at the words, the words in the sequence. We look them up in our embedding dictionary. We get the initial embedding. So far so good, as has been done earlier in the recurrent architectures. And then this part is new. We have three matrices, three trainable matrices, each responsible to generate a representation of that word. All these representations will evolve because these matrices will evolve. So they will evolve to be different from each other, a Q, K, and V, because they're being used differently. And you'll see how soon. Okay, quick recap. You have one representation per word. You need three. What do? You have three trainable matrices. You multiply these matrices by these initial vectors, each corresponding to a single word, and you get three vectors out. Three typically smaller vectors. Okay, so your QI is your query vector I. You have a key vector corresponds to the to matrix K, WK, and you have similarly you have your VI and matrix V, WV, right? Okay. And this is simply how you get your vectors. You may notice that on the left side of these equations, the letters are capital. The reason for that is basically, in reality, what happens is that you don't really, multiply this, matrix one by one by these input vectors. It's a matrix by matrix, multiplication, which is, basically the same thing as your vectors, but they're all together. So basically, you you multiply your matrix of x's, all the words, by w super q, and you get all the q's in your matrix, all the q's, each one positionally corresponding to a specific word, right? Similarly for K's, similarly for B's. So basically all we've done so far is we generated 3 representations out of 1 word representation. And this is to help us to parallelize computation, coupled with the power of attention. Okay, so let us stop here. I'll see you in the next video.